The Wabash River is actually a river of many stories. Pre-glacial incision, glacier meltwater outlet, post-glacial meandering river, prehistoric cornucopia, major transportation corridor, home for coal and oil, and a rich ecosystem. I would like to introduce some of these stories in an emotional scientific landscape to explain why I'm excited to begin mapping there. The Wabash has been a place of dreams and stories since well before Mr. Bodmer sketched his reportedly accurate but seemingly fanciful views of the new frontier. The Wabash drains an area bigger than the Illinois River Basin, and a key emotional and scientific fact is that the river along the Illinois border is generally free to meander within its floodplain. It's here that I tied together my early passion in process sedimentology with geologic mapping, inspired and coordinated with several interdisciplinary studies. Before I came to Illinois to map ancient deposits, I rarely looked at dirt that was more than a year old. Whether mucking in front of Alaskan glaciers or dodging ferries and panhandlers along the Hudson River, I studied sedimentary process and the deposits they produced, presumably to better interpret ancient deposits. In fact, I spent as much time measuring water properties, velocity, salinity, temperature, sediment load, and grabbing sediment before it was deposited as I did studying the deposits themselves. And yes, for those of you with acute vision, Dan Nelson was an important part of some of that work, just about the time when ArcInfo migrated off the mainframe. Known briefly as Skippy, a name that he hated, Dan later earned the appellation of the able-bodied seaman, and he also learned me the value of taking a break. But back on the Wabash, the dominant model of meandering river deposits up through the 1960s called for the simple migration of point bars. That resulted in finding upward sequences of channel, bar, levee, and floodplain deposits. In a lasting contribution to the science, Roscoe Jackson elaborated upon his simple model via studies in the Grayville Quadrangle, the quadrangle that I'm mapping this year. He tied together modern process observations of water velocity and bedform dynamics with alluvial products. Roscoe observed complications caused by the changing flow characteristics that depend upon location within a channel bend and the migration history of each bend. He subdivided flow depositional regimes into transitional, intermediate, and fully developed facies. The resulting stacking of secondary bars on top of scroll bars has important implications for interpretation of meandering river deposits. Importantly, secondary bars can result in coarsening upwards rather than finding upward sequences. Apart from notable stratigraphic studies by Gordon Frazier, very little sedimentological research has been done on the Wabash since the 1970s, at least until the Best Roads group at UI came along. They are performing studies similar to Roscoe's, but with modern tools and the goal of characterizing the ever-elusive turbulence. The deposits don't change so much, but perhaps the new understandings will provide us with new interpretations of the genesis and architecture of the alluvial valley fill. And this is about where we really regret turning in our slides last week. This work was actually initiated by an opportunistic study of a meander cutoff just upstream of the mouth of the river. Here are the cutoff and resulting large sandbars on their way to the Ohio. Although the role of cutoffs in meandering systems is very well recognized, there is much that isn't understood. Why, for instance, only 1 year later did the chute in the foreground capture the flow from the first cutoff? How will the released sediment, an order of magnitude greater load than a normal meander migration, affect downstream processes at the confluence? What if it occurred further upstream? How would neighboring meanders be affected? Many similar cutoffs along the lower Wabash are evident both along the modern course and archived in the floodplain. Our mapping goals include how frequently do cutoffs occur? Are there identifiable forcing mechanisms? How are the cutoffs captured within the valley fill? And what is the infill style of the abandoned channels? And then there are some 300 to 600,000 years of Pleistocene history to interpret. An important story is the well-recognized seismicity in the Wabash Valley, as evident by the Mount Carmel earthquake of 2008. Earthquake activity is partly evident by liquefaction deposits in the floodplain. Gordon Frazier suggested that river planforms and landforms were partly controlled by tectonic tilting. Were they? Those questions might be answered in an interdisciplinary study of other prominent geomorphic and subsurface features that may be linked to seismic activity. Are the elongate features erosional, or is the uncanny association with fault traces and possible liquefaction features genetic? And finally, the recent recognition that the Wabash has migrated enough to expose oil and gas production structures constitutes a navigation hazard as well as an additional opportunity to gauge meander migration rates. As the Wabash Cannonball meanders among storied landscapes imagined, the Wabash River meanders among storied landscapes both real and imagined. The trick is to figure out which is which.